Welcome back, everyone. Before the break, I defined what a convergent series is and what a divergent series is. I'm quickly just going to remind you of those definitions before I define the sum to infinity. A convergent series is where the terms of a sequence get closer and closer to having a value of 0. A convergent series always gets closer and closer to a specific number. So the terms get closer to 0 and the series gets closer to a specific number. A divergent series does the complete opposite. The terms are not getting closer and closer to 0, and the series is not approaching a specific number at all. So hopefully that will make it fairly easy to tell if a series is converging or if a series is diverging. Let's define the sum to infinity. So guys, the sum to infinity is when I have a ratio that is between -1 and 1. So it's a proper fraction, and the ratio does not have a value of a 0. The terms of a sequence approach 0, and their sum does approach a finite number. So this is essentially just saying when I've got a ratio between -1 and 1, the series is convergent. So when a series is convergent, it means that I can calculate the sum of the entire series. So that's quite cool. So if my ratio is a proper fraction, I can calculate the sum of the entire series. So this means that when I can calculate the sum of a series with an infinite number of terms, as it is moving towards one finite number. So guys, I hope that you've clicked that the reason why I can do it is because the series is moving towards one specific number. So that's why I can calculate the sum of infinite terms, because convergent series have terms when added together that converge towards one number. Let's see how we're going to get the formula for this. So what I have on the board is our good old geometric series formula. But now we're going to see what actually happens if r is a proper fraction and when r to infinity is approaching 0. So essentially all that this means is that the terms with this ratio are getting closer and closer to 0. So the sum to infinity will be equal to a r to infinity, because remember I'm taking the sum to infinity, so the ratio to the power of infinity minus 1 over r minus 1. So guys, please remember that my ratio is a proper fraction. And if I take any proper fraction, I could take a half to the power of infinity, or I could take -1/3 to the power of infinity. I'm sure that you guys will agree that as soon as I raise half to any type of power, especially if it's as large as infinity, the number itself is going to get closer and closer to 0. It's the same thing with -1/3. If I'm raising that to an incredibly large number, it's going to get closer and closer to 0. So that means that when I actually have my ratio to the power of infinity, it's getting closer and closer to 0. So the sum to infinity will be equal to a. I'm going to replace r to the power of infinity with a 0, because we know a proper fraction to the power of infinity is going to get very close to 0. Then if I fill in the rest, I'm going to have 0 minus 1 over r minus 1. So let's simplify. The sum to infinity will be equal to -a over r minus 1. But because we don't really like having a negative in the numerator, this formula is commonly written as the sum to infinity is equal to a over 1 minus r. All that I've done is I've multiplied this by -1. Great, guys. Or we know that I can write it as the same thing, because by multiplying it by -1, I'm going to get an answer of this. Sorry, guys, that's not right. Can I just stop it at sum to infinity is a over 1 minus r.
Okay.
Thank you.
Good luck to the ones that can.
Great, guys. So I'm sure you can see that I can calculate the sum to infinity if I have a, which is my first term, as well as my ratio, which is a proper fraction. Let's go to the next slide. So, just a bit of a conclusion for what we have said. The sum to infinity can be calculated by a over 1 minus r if r is between -1 and 1 and r is not equal to 0. So this is your formula for the sum to infinity. Cool, so this example is asking, does the sequence 2, 8, 32, 128 converge or diverge? So we just have to remember the first property of a sequence or a series that converges is that the terms are getting closer and closer to 0. So if I look at this sequence, I've got 2, 8, 32, 128 going on, but I'm sure that everyone will agree with me that these terms are not getting closer and closer to 0. These terms are actually becoming larger and larger and larger. So that is the first property of a convergent series that this actual sequence fails to meet. So we're now going to look at the property of a convergent series getting closer and closer to a specific number. If I add the first two terms together, I'm going to get 10. If I add the first three terms together, I'm going to get 42. If I add the first four terms together, I'm going to get 170. So I'm sure that everyone agrees with me that these numbers are not getting closer and closer to a specific number. 10, 42, and 170 are not getting closer to a specific number. So because the terms are not getting closer to 0, and because their sums are not heading towards a specific number, 10, 42, and 170 are not heading towards a specific number, I can actually say that this sequence diverges. So I'm going to say the sequence diverges. Great, guys. So because it failed to meet the two properties of a convergent series, it means that this series is diverging. Let's look at the next example together. So we have been asked to determine the sum to infinity of the sequence that goes 81 minus 27 plus 9 minus 3 plus 1. The sum to infinity is immediately giving me a clue that I am looking for a ratio that is between -1 and 1. Let's look at the terms and see if there is a common ratio that I can pick up. Just a reminder, everyone, that if I want to check what my common ratio is, I can say that ratio is equal to term 2 over term 1. In this case, term 2 is -27, and I'm going to put this over term 1, which is 81. So the common ratio is -1/3. I'm also going to check this ratio just to double check that I'm happy with it. I can also check my ratio by saying term 3 over term 2, which will be equal to 9 over -27, which gives me an answer of -1/3. So, guys, what I've established is that each term has been multiplied by -1/3 to get to the next term. So, to get from 81 to -27, I've multiplied by -1/3. From -27 to 9, I've multiplied by -1/3. From 9 to negative 3, I've multiplied by negative 1/3. So we are actually going to be able to calculate the sum to infinity of this sequence because I've got a ratio that's between negative 1 and 1. And I can see that my common ratio is not 0. So because my ratio is negative 1/3, I can calculate the sum to infinity. Great, everyone. I hope that you're with me so far. So now all that I'm going to do is I'm going to make sure that I'm happy with what my A value is. I know that my common ratio is negative 1/3. Having my A and my R is going to allow me to substitute into the formula that's going to allow me to calculate the sum to infinity. So essentially, this formula is going to say that if I were to add an infinite amount of the terms of the pattern behind me, this sum would get closer and closer to this specific number. Let's calculate the sum to infinity together. So, for this particular example, we can see that A is 81. Why? Because this is my first term of the sequence. My common ratio, which I have calculated, is negative 1/3. Great. So at this point, I'm now going to substitute into my formula. So the sum to infinity will be equal to A, which is 81, over 1 minus my ratio, which is negative 1/3. We're now going to substitute all of this into my calculator. So the sum to infinity will be equal to 81 over 1 minus negative 1/3. Sorry, let's get this fraction button to work. There we go, negative 1/3. So we can see that the sum to infinity of this particular sequence is going to get closer and closer to 60,75. So the sum to infinity is equal to 60,75. So this is the number of this sequence that the terms are going to get closer and closer and closer to. Cool, guys. I hope that everyone's comfortable with what I've done so far. For the last few minutes, I'm just going to recap what I have done, and then we will see how we're going at that point. So let's revise some definitions. So in this lesson, I've defined a series that diverges. Please remember that a series that diverges is a series where the terms are not getting closer and closer to a specific number, and the sum of the terms in the series are not getting closer to a certain number. So the terms are not getting closer to 0, and the sum is not getting closer to a specific number. A series that converges, the terms are getting closer and closer to 0, and the sum is getting closer and closer to a specific number. We've also discussed that the sum to infinity can be calculated for series that converge by using A, which is my first term, and putting that over 1 minus R. And just a reminder that my ratio has to be between negative 1 and 1, and R is not allowed to be equal to 0.